So I'm shooting for our quiz to be on Tuesday, and I want to cover the quiz. I want to be covering implicit differentiation, and then there's one other small little thing I'm skipping 3.8, and I'm going to 3.9, where derivatives of exponential and log function, which you definitely need to know, which doesn't take long at all. But you know, it's kind of up to you guys. Do you want to? I know you mentioned finishing the sheet. I would definitely like to at least look at together number 13 or 14 of the sheet. So we'll definitely do that, and then I'll leave it up to you guys if you want to. Sure.
So the quiz is just going to be on implicit differentiation?
Implicit differentiation, and I'd like to also throw on 3.9, which is very brief. It's very simple. It's a derivative of exponential and log functions. If we touch on that today, that would be awesome. If not, touch on it Monday. I'm shooting for Tuesday for the quiz. All right, so now 12 you would not know how to do unless you knew the derivative of natural log, which is section 3.9, so don't worry too much if you didn't get that one. But let's start with 11. 11's got a trig function involved there. Sine of 2x squared y cubed is equal to 3x cubed plus 1. Now this particular problem, they could have been a little more clear. They could have actually placed parentheses around this, which I'm going to have to assume that's what it is.
Wait, so what would you mean? Like, it would just be sine of 2x squared or something?
Yeah, for example, you know, if they wrote parentheses around 2x squared, that would be different than that. This is saying the sine of that whole thing, 2x squared y cubed. So I'm gonna assume that they meant the sine of that whole value because they didn't write parentheses. That would be a safer assumption than to assume the sine of just 2x squared or 2, and then the rest, times the rest, yeah. Okay, so here's a good example of chain rule. So the derivative of sine is cosine. So we're going to take, eventually, I know you guys probably don't feel like we have to write this after a while, but I'm just going to write it just to say it, you know, mathematically it's what we're doing. So the derivative of this with respect to x is equal to the derivative of the right-hand side with respect to x. Okay, so the derivative of sine is cosine. So chain rule says, okay, cosine, and then leave this alone for now. Okay. And because we didn't actually really do anything with any of the constants or variables, there's no dy dx or dx dx written as of right now. So it's just, you know, cosine of this stuff, leave it alone. Now, now it's the derivative, I use the word guts. No, it's not mathematics, but here. So it's the derivative of the guts. So the guts is a product. Okay. Now, I'm going to group it, you can group it however you want, but it makes sense to do this more than anything else.
Why would you have to? Because normally, if it was just sine, the sine of 2x squared, you have to treat that like product. You know what I'm asking? So
yeah,
why don't you have to include cosine later when you're? No, I'm like, I don't know how to ask the question.
I'm not sure maybe if you said more.
Because you're using product rule for what is being applied to sine. And normally, if it was just, say the sine of 2x squared, it would be the derivative of sine and then leave 2x squared alone, and then sine and the derivative of 2x squared. So that kind of you kind of like it should be that.
If it's just sine,
Yeah.
then it's okay. Derivative sine is cosine, and then times the guts. I think what you may be saying. Let me show you, because you're asking a good question, because I want to show you what you're thinking of.
Do you understand what?
I think I know
I don't know
what
how to ask you.
I will. Okay, I will write something based on what you're saying. If I had the sine of the cosine of 2x squared. Now this is a case where, from what I'm hearing, where you would do, okay, if I took the derivative of this, so let's say this is y, or this is just y.
She just says
Y, and then you said Y.
All right, so y prime would be equal to, so here's where, okay, the big picture is the sine of whatever, so cosine of, leave the guts alone, cosine of 2x squared
It is true.
times, now the derivative of this would be negative sine, still leave the guts alone.
So you do have this in
So you're working from the kind of like the outside end, the big picture, and so, and then times the smallest guts, which would be 4x. Okay, that's a very good question. That sounded like you were saying something like this.
Yeah, maybe. I don't like it. Yeah, I think that was.
But when it's just this, when it's just sine, yeah, it's just cosine, and then whatever's inside of that, which is this.
Yeah.
All right. Did anyone need more time on this other example that we inside here? Okay. All right. So the derivative of this is cosine now times the derivative of the inside, and this is so you have to see it's a product. So derivative of 2x squared. Now this is just power rule. Is going to be 4x. Consistent. 4x. I could write dx, but I think by now, are you all comfortable with when it's of x? I don't have to write anything because dx is 1-to-1 ratio, which is just 1. Okay. So times 4x. Leave this guy alone. In fact, let me be very careful because this is times going to be the whole what's going on here. So 4x y cubed plus, leave the first guy alone, the first factor alone, 2x squared, times the derivative of y cubed, which is going to be 3y squared dy dx. So, you could just think of it as when I'm differentiating something that involves y, then I need to write dy dx moving forward. I think it was definitely important to know the details instead of just like going straight here.
So can you distribute the cosine?
Okay. So cosine is not something that you can distribute because cosine is like a function of something. Take the cosine of this. Yeah. Now there is some identities that we're not going to worry about now. It's not useful for simplifying, like changing the product to a sum, and I'll see how much you guys have to memorize for the exam. Hopefully it's not too much. Hopefully it's the least amount possible, because some of those are a beast to memorize. But anyway, we're not there yet. That's down the road. What's that? Oh yeah, let's finish the equation here. So equals, thank you. So equals, over here would just be 9x squared. Thank you, Michaela.
Oh yeah, then you divide that. Well, first of all, you can simplify x.
So then now we're just focused on getting dy dx by itself, which is going to be kind of a lengthy process, but you just obey the rules of algebra and disconnect things. However you disconnect them. So divide each side by the cosine of this. So I have 4xy. I said that would be more in there. Let's fix that. 4x. Okay, thank you. 4xy. Take the hall pass, please. 4xy cubed plus 2x squared times. Now this obviously put that together right now. We have a product here, so it's going to be 6x squared y squared dy dx is equal to, if I divide each side by this, I would have 9x squared all over this cosine of 2x squared y cubed. Sorry, I'm saying that's right. And then the next step from here to disconnect this because it's separated by addition. So 6x squared y squared dy dx is equal to this minus this. Should have a little bit more. Kind of get a little snag here. And then the last step would be to divide each side by this. Yeah, you're going to have an issue of a complex fraction, so you may want to combine these. This is pretty nasty looking. So
Can we
let's go.
multiply it by the reciprocal like we did before?
Multiply with that.
You do the reciprocal to get the
Dividing by a fraction is multiplying by a
yeah.
reciprocal.
So when you multiply by the reciprocal x or 6x squared y squared, like a number we did on number 9.
Yeah, we'll end up doing that, but I probably should combine these. I'm going to combine these first. So to combine these, you have to have the common denominator, which is going to be this. So this is going to be, and you know, the most important aspect of this is so that, like, if you have a multiple choice question, that you are able to see it because you can go all the way. That's probably the biggest aspect about this, why it's important. So combining here, we have 9x squared minus 4xy cubed cosine of 2x squared y cubed all over cosine of 2x squared y cubed. I did it all in one step. I multiplied the top, this is like over 1. I multiplied the top and the bottom by this, and then put them together. Because now I can write it all over the same denominator.
But it can't cancel.
No, this can't cancel out with this. Well, because
You don't have in both terms.
it's not all a product. I have this minus this. In fact, I wouldn't want to because the idea was really to write all this as one fraction.
Can you really just do it to just the 4x y cubed, just multiply the top and the bottom?
Yeah, you're allowed to multiply any fraction by the same value, non-zero value, and it'll have an equivalent fraction.
It doesn't mean the whole thing?
Well, I did. This is over 1. This guy, maybe you're saying this guy is already over this? He's already over this?
Mr. Gross.
Hold on.
It's good. Yeah, I'm good. What are you multiplying? I'm multiplying 4x y cubed by 2x squared y cubed over 2x, or the cosine, sorry. Cosine.
Okay.
So it's multiplying that by 1 so you can get a common denominator.
So you can cancel it out.
Yeah.
Okay.
I just want to sound like that.
And then now the last step, dy. Someone's going to ask me something over here? Yes.
Why do you have to combine, why can't you just leave them separate? That's what I did, I just leave them separate.
Yeah, the only thing, and I would be fine with that too, but the thing is that we need to find dy dx. When we end up dividing by 6x squared y squared, it's going to be a nasty looking complex fraction. And so let's say this is a multiple choice question on the AP exam. And you would have to recognize, in case because they're probably not going to leave it as a complex fraction. I can probably say that. So you would need to be comfortable going all the way to see what it looks like, which is where we're at now, which is going to be 9x squared minus 4x y cubed cosine of 2x squared y cubed all over, because I basically multiply both sides by 1 over the reciprocal. So we have 6x squared y squared cosine of 2x squared y cubed. That was a doozy. Alright, so that was that.
Why did you have those lines on top of that?
Multiply what?
It's the cosine is 2x squared y cubed onto the top of that. Why did you multiply that by 9x squared y squared?
You want to know why this is here?
Yeah.
When I was here, this I can view as technically over 1, and I had to combine two different fractions.
Okay.
So I multiply the top and the bottom by the least common denominator, which was cosine,
Alright.
and then put them together as 1. Yeah. So this would, again, just to emphasize, this would give you the slope of any tangent line for any point x, y that is part of the domain and range of this function.
When you were doing this, they would go down and they follow your work, and if they saw you do something right, they give you a check mark. And
Yeah.
the ones that were longer counted for more points. But
Oh,
if
yeah.
you only did up to like half of it right, they give you points for that half.
Oh yeah.
In calc, it's like they just want the answer right. They don't care.
Oh yeah. Well, okay. Well, AP Calc exam has a free response section, and they definitely get a partial credit, which is good. But in terms of the multiple choice, yeah, that does kind of stink that.
Well, it was the same
They're
for
not-
ACE, but ACE really focused on like
The free response.
credit for what you did right.
Did they have more free response on it?
It was all.
It was all-
Oh, okay.
There's no multiple choice.
Okay.
So.
I would actually probably prefer that myself.
Yeah. So what I'm also curious about, so when you divide both sides by 6x squared y squared, like for that last step right there,
Yes.
how come you're not dividing that whole entire fraction by that? Like why can you just?
Well, to divide by a
It's
number.
multiplying by reciprocal.
Yes. Yes. I didn't make a mistake. I don't think. Just
Yeah,
very
because
careful.
I got the percentage.
What's the thing about? Can you remind me of the whole exponential and logarithm? Unless there's another one.
Yeah, and we'll tell you that we'll do that, and then if we have time, I would like to show you how to end up taking the second derivative, which is number 13 and 14. So let's go ahead and move on to 3.9. So for numbers 13 and 14, what you would want to do, yeah, you would just take it again.
Yeah.
Sometimes if you can get y written literally from the given equation, then you would need to definitely plug that into y.
Take your y and it's just do the idea.
All right. 3.9, if you have a text, derivatives of exponential and log functions.
Oh, we're learning a lesson now? So will this section be on desktop? Yeah. No.
So here's the two that you have to memorize. This is just like the title card. So these are the two guys we'll be looking at. And yes, I agree with Caleb. Alright.
I don't know how well you'll understand that. Yeah, so right now, he's right.
It's a nice guy. Use the variable. So like, why are you crushing my fingers? Leave all his room.
Subclass and log.
The ego class is
I mean, it's supposed to go in a lot longer, but it's more than an hour and a half.
Yeah, about an hour and a half.
That's the longest I've ever been in.
That's the natural way. How do you take this? It's funny that you do like little slanty fractions because a lot of math teachers say don't do this fractions.
Oh yeah?
A lot of my teachers will say no. Yeah.
Why is that?
I
Is it
think
less
it's
clear?
No, it's not. Wait, if you use a differential function what does that mean?
You use a differential function of x, so it could be a lot of different things. It could be polynomial functions.
Okay, so it's like a function. It's not a number.
Yeah, it's a function. It's specifically, should definitely be differentiable for this whole.
Right, okay. First I know
So what we'll do is we'll look over this, some examples, the other one's an example. Okay, so there's this one. And the other one you have to know is log. that's too close to the back.
It looks like homework.
Now I can see that every time I look at it.
I thought you took.
What do you guys
The bottom.
Same times too. Good idea. Why am I multiplying sentences then? I was thinking I'd get back to my own like,
So an example they give on page 173 is a good example. Well, first we'll go over the first one. Did you bite for this? I'm sorry. It stinks. It does. What did I do? It does stink.
What page are we looking at?
We're on page 173. I'm sorry it hurts. So, I wonder if I should just start with something that's a little more, shows it.
Yeah, I don't understand what you just wrote on the board.
I know,
Like, you
I know.
didn't say any words about it.
Alright, yeah, so, alright, so this is saying, like, imagine you just have, like, some A is a constant. Some constant to any sort of differential function of x, whether it be sine of x, x squared, x cubed minus 6x, any sort of differential function of x. Derivative of that is equal to that original guy times the natural log of the base times the derivative of the differentiable function with respect to x. And it usually when you see an example, it's like, oh, okay, it's easier because the u kind of throws. But they're saying just u is any differentiable function of x. And I'm going to show you guys some examples. Yes.
Why is it du over dx and not dA over dx?
Because it's the derivative of the
Because a is a, well, because this is how it's defined, but a is a constant, but you end up having to deal with this.
It's like 6 to the sine.
There's a proof for this, but it's not necessary to go over it at all. You do not have to, there's no proofs whatsoever. There are no proofs. So, that being said, so let me give you an example. So, let's say you had to do, you had y equal, this is example 2, if you want to follow along. On page 173. Let's say you have y is equal to 2 to the power of t minus 3. So then y prime I don't even know why I had to throw on that minus 3. I really don't want to focus on it all. Okay, so this. So the derivative of this, according to the formula, is, okay, 2 to the t times the ln of 2 times the derivative of that with respect to whatever variable we're concerned about. So it would be 2 to the power of t times the ln of 2 and then, okay, so then the derivative of t with respect to t is just 1, so we technically do this, and then minus 0. What was the question about the quiz?
Oh, like if we were to do this on a quiz, would you care if we put, like, is it easier for me to see it if I put parentheses around them? Like, so like I did parentheses around like 2 to the t,
derivative of t with respect to t is 1.
Well, yeah, but what if it was a lie?
Why? Well, I mean, technically you can think of it as power rule. Okay, 1 to the front, drop it down, t to the 0, and so 1 times t to the 0
So if it was 2 to the t squared, it would be 2t.
Yeah, that's why I want to do a different example. I'm going to do one that covers more than this, so to speak.
So confused, why wouldn't it be like dt over dy? Why is it dt over dx?
dt over dy. Okay, yeah, so this would be, so let's go ahead and, you know what, let me just do this. That's even more,
So then you leave it like
more detailed.
Or dy over dt.
Yeah,
That makes more
yeah.
sense to me.
Mhm. There you go.
So then how do you come up with the 1?
Well, what I ended up doing technically was taking the derivative with respect to t of each side. That's why this is dy dt. Okay, well, look, what's the derivative of t with respect to t?
Oh, it's 1.
1. It's like that previous problem, the dx over dx scenario. Same exact thing, yeah.
So if this problem had been dy over dx, if we can't find dy over dx, would then t just be dt over dx? Or the derivative of t?
Yes, very good. What you get would be dt over dx. Where it's like, okay, t may be, we're assuming if it is a differentiable function of x, you have to dt, or wherever that is. So we say, okay, dt over dx.
Okay.
Good.
So if you're doing something like a derivative with respect to whatever, that's the thing that's being respected of the problem.
Yeah. No, that's exactly right.
Okay, cool.
That's exactly right.
x in this case.
What's that?
So t is the x in this case, because that's du over dx in the equation, but because the t is used as the x, it's dt over dt.
Yeah, t is the independent variable. I'm going to do an example that is x, because I think we naturally feel more comfortable with that. So this is, of course, we just did 2t ln of 2. Okay, so let me show you what I would think would be a little better example.
And then the 0 was the derivative of 3, right?
Yes.
Okay.
So let's say you had a y is equal to 4 to the power of x squared minus x plus 1. Okay? So according to this, dy dx would be equal to this guy as he is, right, a to u, times the ln of 4, yep, ln of 4, times the derivative of this with respect to x, which would be 2x minus 1.
And then are we supposed to?
And you could, if you want, that's perfectly fine. It's all multiplication.
Do you want us to like solve it for the natural?
No, it's going to be some nasty, irrational value, something with ln of 1. Of course, you could reduce ln of 1, that's 0, or, yeah. One more example involving, let's say, a trig function. Anyone need more time on the slide?
This was like squared, this whole thing was just squared.
Let's say y is equal to 5 to the power of the sine of x squared plus 5. And you want to define dy dx. So, right as it is, leave it alone. Times the natural log of the original base times the derivative of this, which would be equal to, now chain rule, cosine of x squared plus 5 times the derivative of the guts, 2x.
That's so much like, it's just so much. That is longer than the actual problem.
It's like chain rule kind
Yeah.
Just, I would say,
It
just be careful, look at piece by piece.
Yeah, so really the only thing that You're still just finding the derivative, you have this equation there.
Mhm. So you have to know the formula now. Alright, so now we can look at a couple examples to go with the derivative of log. So let's say you had y is equal to the log of base 4 of u will make u 2x cubed minus x. Okay. So this is the other one, right? So now we're doing, before we were doing the derivative of some constant to some power that's a differentiable function of x. Now we're doing the derivative of log of whatever base of some differentiable function.
Will you rewrite the other equation? Really quick.
Side by side, yeah. You do that.
I have it, but.
Yeah, you have it. Whatever you think.
1 over ulna times.
Oh my god.
U, L, and A.
Yes.
So,
Oh, y prime equals, wait, I don't know how to read this.
I'd like to, if we're going to do that, we're going to write the whole thing.
D
Let
over
me just,
dx equal, or d over dx times log base a u.
oh, thank you.
Equals,
The derivative.
Okay, of log base a of u.
yes,
Uh-huh.
equals 1
Uh-huh.
over ulna.
Natural log of
U
A.
ln of A.
Natural log of a times
the derivative.
du over dx.
Okay.
Good God, Kate.
Okay. So that's what we're going to do.
DA, I thought it was.
Yes?
I thought it was DU over DA, that's what I had written.
DU over
No,
dx.
it's dx.
Should not be DA.
No, wait,
Where did I wrote that?
I don't have time for another example.
Because I would have had that in my notes.
Sure, we only like 2 months.
Thank you.
Okay. So, and again, I was going to have Monday just be a continuation review.
Okay, sounds good.
So here we have 1 over u, so 1 over 2x cubed minus x, that whole thing times the ln of a, times the ln of 4, times du dx.
Can we just wait to do this one on?
And du dx would be 6x squared minus 1.
Where is it? Times the inner, right?
Well, couldn't you just substitute the x
Yep, absolutely. So yeah, to look even cleaner.
Okay, yes. Okay. 1 over ulna. That makes so much sense. I'll remember that. Times the inner.
1 over all that.
It's just math, we were doing math, so it's not saying
So I'm thinking maybe a worksheet on this would be good for Monday.
Honestly, just like doing it over.
Is it